Good morning, students. In the last class, we discussed about the hydrolysis of salt, different types of salts, what are acidic salt, what are basic salts, what are neutral salts, and how these salts undergo hydrolysis. What is happening when a salt of strong acid and strong base undergo hydrolysis? We found that when a salt of strong acid and strong base undergo hydrolysis, a neutral solution is obtained. Similarly, when a salt of weak acid and weak base undergo hydrolysis, a neutral solution is obtained. When a salt of strong acid and a weak base undergo hydrolysis, then an acidic solution results with a pH less than 7. So when salt of weak acid and strong base undergo hydrolysis, then a basic solution results with a pH value more than 7. So this we discussed, and also we discussed how this hydrolysis is going on. We discussed about the hydrolysis constant. Okay, how to obtain the hydrolysis constant, and finally we discussed about the solubility product. What is solubility, and how the sparingly soluble salts undergo ionization, and how the ions formed from the sparingly soluble salt and the undissociated salt are in equilibrium. That will be discussed. How to obtain the solubility product constant, that also we discussed. So, as per the last class, if we have a salt like AXBY, in XBY, we are getting what? XAY plus YB X minus. Okay, XAY plus XA power Y plus YB X minus. Where if solubility S mole per liter, solubility is S mole per liter, S mole per liter. Here we can get what X S mole per liter and Y S mole per liter. So because 1 mole of AXBY is giving X mole of AY plus and YB mole and Y mole of BX minus. So if S is the solubility of AXBY, that means S mole of AXBY will dissolve, then we will get XS mole of AY plus and YS mole of BX minus. Okay. Now KSP we obtained. What do you know? AY plus power x to BX B power x minus power y. So AY plus is how much? XS, the XS mole power what? So this is how much? YS power y is equal to what? X power x, S power x, Y power y, S power y equal to what? X power x plus y, X power x into Y power y, S power x plus y. So KSP is equal to what? X power x into Y power y into S power x plus y. In this way, we can obtain the KSP. Okay. Now, what are the applications of this solubility product? Applications. First of all, we can calculate the solubility of a sparingly soluble salt. Okay. Calculation of solubility of sparingly soluble salt. Okay. So here already we obtained here Ksp is equal to x power x into y power y into s power x plus y. So what you can write? S power x plus y is equal to Ksp divided by x power x into y power y. Okay, or S is equal to Ksp divided by x power x into y power y whole power 1 by x plus y. So in this way, we can calculate the solubility of a sparingly soluble salt. Here I have taken the AxBy as the sparingly soluble salt. So this sparingly soluble salt AxBy undergo ionization into XaY plus and YbX minus. Okay. Let the solubility of this salt is S mole per liter, say we have taken. So from this stoichiometric, 1 mole of AxBy is giving x mole of Ay plus and y mole of Bx minus. So therefore, when S mole of AxBy will dissolve, we will get value xs mole of Ay plus and ys mole of Bx minus. Okay, so as per the solubility product quotient, Ksp will value the product of the ionic concentrations of this Ay plus and Bx minus. Okay, so Ay plus power x and Bx minus power y. But here we have seen value when S mole of AxBy will dissolve, we will get what? Xs mole of Ay plus. So Ay plus is equal to, I will take here xs. So xs power x, ys power y. That means x power x, y power y, s power y. So Ksp is equal to x power x, y power y and s power x plus y. So from this, if I take s power x plus y, we will get what? Ksp divided by x power x and y power y. Now s is equal to what? Ksp by x power x, y power y whole power 1 by x plus y. So in this way we can calculate the solubility product constant. So let us have some numerical basing on this solubility product constant and the calculation of solubility also. So basing on this formula, S we will have some numerical, and basing on this also we will have some numericals. Okay, let us have some. Okay, so let us see this numericals. Calculation the solubility of AgCl is 1.31 into 10 power minus 5 mole at 20 degree centigrade. Calculate the solubility product. First of all, you have AgCl, can give value Ag plus plus Cl minus. Okay. Now, here you see x is what? 1, y is what? 1. Okay. And the solubility of this is 1.31 into 10 power minus 5 mole. That is what? S is equal to 1.31 into 10 power minus 5. Therefore, Ksp is equal to x power x into y power y, s power of x plus y. Okay, so this is equal to 1 power 1 into 1 power 1 into s power of 1 plus 1. What is x square? Okay, so Ksp equal to what to S square. And how much given here? S 1.31 into 10 power of minus 5 square. Okay, so we will get the answer 1.71 into 10 power of minus 5. Clear? Question number 1. Now question number 2. The solubility product of FeOH3 FeOH3 will get what? Fe3 plus 3OH minus. Fe3 plus 3OH minus. So here x is equal to 1, y equal to 3, and s is given how much is the solubility product of it. So Ksp given equal to how much? 1.1 into 10 power of minus 36 mole to 25 centimeter. Now for this equation, Ksp is equal to, already we have derived the equation, Ksp is equal to x power x, y power y, and s power of x plus y. Okay, so here x is how much? X is 1, so 1 power 1, 3 power 3, s power of 1 plus 3. 27 s of 4. How much? 27 s of 4. So Ksp is equal to 27 s4, therefore s is equal to Ksp by 27 whole power 1 by 4, or s is equal to Ksp how much? 1.1 into 10 power minus 36 by 27 whole power 1 by 4. Okay, so this on calculation we will get what? 4.8 into 10 power minus 8 gram per meter. Okay, then you know number 3. Number 3. In the case of MgOH equal to at 298 Kelvin G this much. Okay, so Ksp equal to what? 1.4 into 10 power minus 11 mole. What is the solubility of MgOH2? Okay, now MgOH2 magnesium hydroxide will give what you know? Mg2 plus also 2OH minus. MgOH2 will give what? Mg2 plus also 2OH minus. Okay, you will see x equal to 1 and y equal to 2. So Ksp is equal to x power x, y power y, x power of x plus 1 equal what? 1 power 1, 2 power 2, x power 1 plus 2 equal what? 4s. Ksp equal to 4s. Therefore s is equal to Ksp by 4 whole power 1 by 3. Okay, how much Ksp here? 1.4 into 10 power minus 11 divided by 4 power 1 by 3, which is equal to, we will get what? 1.518 into 10 power minus 4 mole per liter. Okay, so simply you write the equation MgOH equal to will give you what? Mg2 plus 2OH minus. This is the stoichiometric equation. Now once you write stoichiometry equation, so now find out the coefficient. So here the coefficient is 1, here is 2. So x equal to 1, y equal to 2. Now case b equal to what? X power x, y power y, s power x plus 1. Put this formula. Now put the values of x and y. Okay, and finally we can get now s equal to what? S by 4 equal to 1 by 3. So we will get this answer, right? Number 4. Number 4. The solubility of Ag2C2O4 is this much. Calculate the Ksp. Now Ag2C2O4 will give you what? 2Ag plus C2O4 to 2 minus. Okay. So 2Ag plus C2O4 to 2 minus. So here you can see the coefficients. Coefficients here is 2. So x equal to 2, y equal to 1. Now Ks is equal to x power x, y power y, s power what x. Okay, then we have x is 2 here, so 2 power 2 into 1 power 1 into s power 1 plus 2 equal to what? Again 4s cube. Okay. So find out the solubility. So again s equal to what? S by 4 or 1 by 2. How much Ks be here? The solubility of Ag2C2O4. So we have to find out here the Ksp. So Ksp is equal to 4 into solubility S 1.1 10 power minus 4 cube. This will get what? 5.3 10 power minus 12. So 5.3 into 10 power minus 12. So in this way we can calculate the solubility and the solubility product constant, right? So this is one of the applications of solubility. Now next, application number 1, calculation of solubility and solubility product constant is over. Now next we will calculate what? Prediction of prediction of precipitation of reaction. Prediction of precipitation of reactions or prediction of the ionic equations, ionic reactions. Let us see. Normally, for an electrolyte, the ionic product never exceeds the solubility product. However, if the ionic product exceeds temporarily for a while, then precipitation of the reaction will take place. So if Kw ionic product of the electrolyte is more than KSP, the solution is supersaturated and precipitation takes place. KW less than KSP, the solution is unsaturated and more solute can be added. Therefore, KWC is equal to KSP. The solution is just saturated. Okay, so in this way we can predict whether in a electrolytic reaction, so whether precipitation will take place or more solute can be added or the solution is just saturated. Okay, so remember here, if the ionic product value Kw exceeds the KSP, then the solutions become supersaturated and precipitation will take place. Okay, next one. Number 3, qualitative analysis. See, we have different kind of cations. We have Na plus, we have K plus, Ca2 plus, Ba2 plus, Zn2 plus, CO2 plus, Pb plus. So these ions are present in the form of the salts. So in a particular salt, what kind of ion is present? Whether Na plus or K plus or NH4 plus or Zn2 plus or Pb2 plus or Cu plus, okay, Ba2 plus, Sr2 plus, what kind of ions are present there? To detect, we have certain process called the qualitative analysis of cation. So these different kind of cations are categorized into different groups, and for each group we are having the different kind of reagents, and to find out this kind of group cations present, solubility product concept along with common ion effect concept combinedly applied. So here we already know about the solubility product. So let us discuss about the common ion effect. Then after we will apply the concept of common ion effect and solubility product combinedly for the qualitative analysis of different kind of cations. Okay. So now the common ion effect. Common ion effect. What is the common ion effect? See, suppose we have a weak electrolyte like ammonium hydroxide, NH4. This is the weak electrolyte. It undergo Figli ionization into NH4 plus OH minus. Okay. So ammonium hydroxide NH4 is under ionization into NH4 plus OH minus. And now if I will add at equilibrium, if I add a strong electrolyte, this is a weak electrolyte NH4 so undergo field ionization into NH4 plus and OH minus. Now when we add NH4Cl ammonium chloride, we will get what? NH4 plus Cl minus. So it's a weak electrolyte. It's a strong electrolyte. Now when we add a strong electrolyte to this ionization of weak electrolyte when in equilibrium, and this strong electrolyte contains an ion which is common to this ion of the weak electrolyte. See, NH4 OH is giving NH4 plus OH minus, and I am adding the strong electrolyte NH4Cl which is giving NH4 plus, and this is a common ion to this one. This one. Common ion. So when you add an amount NH4Cl, the concentration of NH4 plus ion is increasing. And because this NH4 plus ion concentration is increasing, according to Lee-Jacques principle, the concentration of the product side is increasing, therefore the reaction will go backward. That is what the rate of decomposition of this NH4 OH will suppress, will reduce, and this suppression of dissociation of the weak electrolyte by the addition of a strong electrolyte containing its own ion or common ion, which is called common ion effect. Okay, so what I can write? The suppression of dissociation of a weak electrolyte by the addition of a strong electrolyte containing its own ion is known as common ion effect. Okay, so here you see this is the weak electrolyte, it undergo ionization, and then after this is the strong one I am adding that contains its ion also, and this indicating the concentration of this NH4 plus ion, and I could resolve this principle because here the product side concentration is increasing, so the reaction will go to what? Go to backward. Okay, so that we see the suppression of the dissociation of this electrolyte will be reduced, and this reduction or suppression is called what? The common ion effect. And this common ion effect is having many more applications. Okay, applications of common ion effect. Common ion effect application. So So first of all, salting out of salt. Here you see, we have this salt C17H35 COONA. Salts are generally your sodium salt of higher fatty acids like palmitic acid or oleic acid, like C17H35 COONA. So this is a what? This is your salt, sodium salt of higher fatty acids, and this on top of what, C17H35 COO minus also Na. Now here if I add small amount of NaCl, okay, it's a weak reactant. If I add a stronger one NaCl, and this will be what, Na plus Cl minus. That means see, so when I am adding this strong chloride NaCl, I am adding the ion which is common to its ion. It's an Na plus, and this I am adding Na plus. So what happens? The concentration of this Na plus I am increasing. Okay, and according to Richard's principle, because the concentration of this product side is increasing, so the reaction will go backward. So more and more salt will precipitate out. This dissociation will suppress, and this will undergo precipitate out. Okay, so this is called salting out of salt. Okay, so the salt solutions which we have prepared, C17H35CONA. So that's contain the weak chloride. This one is weak, and when I am adding its common containing its common NaCl, what is happening? The concentration of the product side is increasing. So the dissociation of this one is suppressing. The reaction is going backward. So more and more amount of this salt will precipitate out. Okay. Similarly, purification of NaCl. The NaCl which we are getting from the seawater, okay, that NaCl, you see, Na plus Cl minus. If I add HCl, your H plus Cl minus. Okay, so when I am adding HCl, that is will contain the common ion Cl minus. So this concentration, okay, will increase. Okay, so because the concentration of this product side is increasing according to Richard's principle. So okay, due to the common ion, the dissociation of this NaCl will go backward, and you see more and more NaCl will precipitate out. This is called the purification of your NaCl. Okay. Now, NO what will happen here? Qualitative analysis. Okay. So, in qualitative analysis, so the concept of common and effective and solute product both will be applied, which will be helpful for the precipitation of preferential precipitation of different kind of group cations, and this we will discuss in the next class.